Okay, today is September 26, 2020. Let's continue to our class. We were doing, as I said, some micromechanics. In this subject, there are two main goals. One is to achieve or calculate the homogenized material property of the UD stiffness, and the other one is to calculate stiffness amplification factor, or you can call strain amplification factors, depending on the applications, from which you can directly calculate fiber and matrix stress from UD ply stress. Okay, let's review ourselves what we did last time. Okay, this was stress amplification factors for UD in one directions, and we use rule of mixture in x directional stresses, and in x directional strain, fiber and matrix strain are same as the UD fiber directional strain. These are equations of the rule of mixtures. Very simple, but very important equation to understand the behavior of the composites. From these two equations and also a constitutive equation, well, this looks a little bit messy, but let's see here. The fiber, we have a constitutions, fiber stress and fiber strain, and in one-dimensional case there is a stiffness. For the matrix, also matrix stress and strain, and this stiffness. So again, these two equations can be called rule of mixtures, and these two equations are constitutions of fiber and matrix. And if this one, I would say these equations can be put here, and this one goes into here, and then this stress and fiber stress and fiber and the matrix stress and goes to here. So as a result, we have this, and we simply have a epsilon x and fiber directional stress and stress and strain, and by definition, this is the EX stiffness in extraction. Now, the stress amplification factor, we like to, again, the definition of stress amplification factor is to relate between UD ply stress and fiber stress. So this is called M11 factor in the matrix. And this term is derived from these relations. And this relation is, by the way, obtained from all the procedures. And so this one is called M11, M11. And similarly, we can have the N11 for matrix. So this is the case for the fiber, and this is the case for the matrix. So this is the matrix one. Let's take a look at these two relations. After we drive this relation, we always like to see the numbers. So given, of course, the given, oops, okay. Given property is the EX fiber here. There's only one-dimensional quantification for fiber and matrix, so we just have a EF and EM. So EF and EM and fiber volume fraction, let's call VF. VF are the major given factors in micromechanics. So EF usually, I mean, it can depends on the fiber property like carbons and glass, but let's choose 300 gigapascal. So 300 gigapascal, and matrix, let's say epoxy, then about 33 or 35 gigapascal. No, not the 30, about the 3.3 gigapascal. And volume fractions of the fiber is usually is ranging from say 0.4 to 0.6. In this case, let's choose 0.6. And here, I like to define the name created from selections. So left column will be the name of these cells. Okay, then as you can see, this cell will automatically has the name of EF because we selected and we assigned the name. So left column will be a name of the right-hand side columns. And this one, EM and MVF. Okay, so this is the easy way to assign the name. And I very strongly urge you to use name rather than address. Address means that, say you want to calculate some value, and you can of course say use D2. You can use a D2 times 2. What is this? Okay, so this D2 times, sorry, D2 times, I don't know what's happening here. D2 times, you can multiply any numbers here. But this D2 does not have any name. So I always, as I said, recommend you to use a name instead of address. So in this case, EF. Then as the equation become complicated, you still have the meaning of each cell. So again, use name of each cell rather than just address, okay? Okay, purpose, what we like to do is to calculate a stress amplification factors. Here, there are two I don't know what's happening here. EX, now EX is given as EM times VF plus EM times a 1 minus VF, which is the VM. So this is the value. Okay, this is the value. And now stress amplification factors, M11F, fiber 11F. This is the term, as you can see here, equal a EM divided by Poisson's ratio VF times EF plus EM. EM is given as 1 minus VF times EM, right? Okay, so this is the stress amplification factors. And now, how about the E11M? E11M is here, this equation in yellow. All we need to do is just change this F, right? I mean, M. No. Okay, so this one matrix is the M. And this fiber, sorry, fiber is the, this will be a F, right? And by the way, the this is the equations. As you can see, please pay attention to these values. When this value, fiber stiffness gets increased, see what's happening. Very high number. See what is going on, these two factors. Well, it's not that easy to observe, but as you can see here, first of all, M11F, this yellow one, if EF is larger and larger, then this is nothing but 1 of VF. very close to 1 of VF. See how close they are. Again, here, when EF gets increased higher, much higher than EM, then this term will be neglected compared to this term, and this and that eliminate, and so this steep stress amplification factor will be nothing but 1 over a VF, okay? So, and when VM, this gets very small and smaller, and this will be very close to 0. I mean, extreme value. This is the extreme value for EF, which is much bigger than EM. That's usually what's happening in composites. So stress amplification factors, if you don't know the material property of the fiber and matrix, you simply say inverse of the fiber volume fraction. That is the stress amplification factors. And matrix wise, there's no stress transfer to matrix. I'd like to discuss about this by, physically. Let's say we have a fiber and we have a matrix, right? We have a matrix and fiber. But something like that. And then we are applying some external force. External force will be applied to here and applied to here. We can call this is the sigma x. Now, what we like to do is that how much the force we transfer to this fiber. So let's say this fiber, and this is the sigma x in fiber. So by definition, sigma xf M11F sigma x, right? So again, how much stress will be transferred by the fiber when this ply subject to a sigma x? And imagine that Ex, imagine that fiber stiffness is much bigger than EM. Then what will happen is that this UD, by the way, is always expanded together. This ply is always expanded together, right? Expanded together means this is the epsilon x. expand the same amount. When these expand the same amount, stiffness is very small in matrix. So the force transferred by the EM, by the matrix, can be negligible. So again, the stress transferred by the resin will be very small and smaller and smaller. So only stress are transferred by the will be transferred by the fiber. So fiber is the only one transfer sigma x. This is the sigma f, right? And then, but the point is that this dimension, the size is remain as the fiber volume fraction. So cross section of this is the still remain as the VF. So VF times sigma F will be simply sigma X, right? Because there are no force transferred by the resin, only the stress is transferred by the fiber, and these are the relation. This is the equation is left. So as you can see, sigma F will be just nothing but sigma VF, I mean the 1 over fiber volume fraction and sigma X. So this is the M11F when EX is much larger than EM. That's usually what's happening in the composite. So most of a value like 0.6, you can see about the 0.5, and this will be 1.97, and this will be very close to a 2, and so on. This is the real value of the carbons and the epoxy, and this is the fiber volume fractions. Okay, and the this is very useful in understanding composite mechanics. Okay, back to here. So this is the stress amplification factor, and now how about the resin dependent direction, EY, I mean the transverse directions. And from rural mixture, we had these equations. So Young's modulus EY is given like that. And in this case, the stress amplification factor is very simple because we assume sigma Y of the fiber, sigma Y of the matrix is the same as the a unidirectional sigma Y. So when this applies a subject to a transverse direction, all the stresses will be just transmit and will be the same as the sigma Y, okay? So this one is nothing but the stress amplification factor. Here, as you can see, this one is the same as the sigma Y. Again, we have this stress, and that stress will be the same as the external ply stress. So they are all same. So from this and that equation, by definition, we have this is the 1, because sigma YF equal M 22 and sigma y. So here is the will be just a unit value. And we can also easily get this value for the I'm using the Excel. But here we need to understand the meaning of the EF and meaning of the EM. EF is the one of the fiber stiffness, but in the transverse direction, right? Transverse direction. That's the one thing we didn't distinguish in derivation, so we need to be careful. So EF, and there is another one, EYF and EMYM. Basically, EF is the same as EXF, fiber directions. EM, I would say EXM. But in transverse direction, we could have a different material property, but so we need to define. Here, EYF, fiber directional transverse stiffness, is not well-known value, but very weak, especially in carbon fiber. Transverse stiffness is relatively weak. So I would say it's the order of the resin. So we can say E9. And EYM matrix is always isotropic, so this will be the same as that one. And then we assign the name here. And now we calculate EY. EY, you know, EY is inverse Rho mixture. So this will be 1 over VF divided by the now here, when we calculate, you need to use this one, and plus now we need to have this, and then 1 minus VF divided by EYM. Okay, this is the EY. And again, this EF is the transverse directional stiffness, and this is a transverse stiffness, and VF and VM. Right, this is the inverse. Now, M11, now M22F and M22 matrix will be just nothing but 1 as we derived. and this will be a let's define the name. Oops, like that. Define the name. Okay. Okay, so this is what we derived from our, these two slides. And how about the shear directions? Okay, shear direction. In shear direction, the derivation is very similar to y directions. This is the fiber and matrix and matrix and so on. Now the in-plane stress sigma s is applied to here, Then as you know, deformation will be something like that, because this is the stress we are applying. And matrix will have a certain deformation and fiber will have a certain deformation. But regardless of a material, regardless of a fiber volume fraction, this matrix will have subject to a same stress as the ply shear stress. And this fiber, while it may have a higher or different stiffness, and this deformation may differ from a fiber, but this is the sigma shear matrix. This is the sigma shear, the fiber, but this is all same as the ply shear stress. Ply shear stress usually in tensor form, we call them sigma xy, but anyhow, they are all same. And deformation-wise, deformation is something like ES, ply level shear stress, and ply level shear, the shear strain is the deformations along, this angle, right? This angle. But this is not a straight because each one has a different stiffness. So this is something like that and something like that and something like this. Then average wise, because considering the length and considering this shear deformation of each matrix and fiber, and we can easily have the overall shear strain will follow the rule of mixtures. We can drive one by one, but this is the very well known. Similar to like that. Okay, similar to exactly the same as that one. So this is the strain in ply level. And now combining this and also given the constipations, epsilon xf equal E S fiber sigma SF, and epsilon SM equal ESM and sigma MF. So always keep in mind, please, this is the rural mixture, and this is the constitution. Those are two governing equations have to be considered in deriving micromechanics: stiffness, homogeneous, and stress amplification vectors. And we can easily reach this equation. Well, again, you need to keep driving. Simply, like put this one into here, and simply put this one into here. And then you have a sigma m and sigma f. They are all same. So this will be a sigma s. We can easily have this term. And also this is the, by the way, as I said, exactly same as the transverse direction. Sigma f fiber and sigma s applied stress will have a factor of 1, right? So I will repeat here. S is a 6 component, and fiber and sigma s ply level, and so this will be a 1. So we can also program this. I will say shear, and this one I will say shear, and this one S, and this one let's call sigma M66, and sigma, the M66M, right? And here, this one, instead of these terms, we can simply have these terms. Instead of EYF, you can say these terms. Oops. Before that, let's give the name. Select, oops. Select and give a name from a left column. And by the way, we do the same thing here. So ESF will have here this, and EYM will have this. And MFF, M6 and M6F and M will be the 1, okay? So again, I would like to divide like this, and this is the homogenized stiffness. This is the stress amplification factors for, I would say from here it is the X directions, which is the fiber directions. And here is the Y directions, usually called matrix directions. And shear direction is called S. Okay, S means shear. It's also a matrix dominated directions. So I like to get rid of these terms. And as you can see, now extreme value for, let's delete those terms. And I like to okay. I like to separate these things. That's okay. And the I will say this is the matrix volume fractions, and let's give a name and formula left. And this one is nothing but 1 minus VF. So there are many terms. 1 minus VF is nothing but the VM, right? So let's call this one, we can just simply replace by the VM. So equation now looks much simpler. I would like to show, okay. I like to show the equations, okay. This is the how you see formulas, and each cell, this rather than giving us the value, this is the how you see the equations, okay. And this is the EX, and from here, and this and that. And EY is given like that, and this and that, and so on. Oh, by the way, we have a wrong value here. And EM is not the ESM. Out. Usually, matrix is the isotropic. Isotropic means that we have a insert. We have a Poisson's ratio. Poisson's ratio. I would say let's call Poisson's PF, because it's confused with VF. So let's call Poisson's ratio PF. No, sorry, not here. It is okay. PF, say 0.3. Usually that's the one we have. Fiber. I'll call V. V stands for the. I mean, not the V. It's a new. But here I'll call V PF. And the here Poisson's ratio matrix, and give a name, and give a name. And also this is about the 0.3. Now for matrix shear modulus will be I mean, since it's isotropic, you can say matrix divide and the Young's modulus divide by what? 2 times 1 plus mu. That is the this guy Poisson's ratio. This is the how we calculate the shear modulus of the isotropic material, right? And then what else? Okay, so ES given from this value and this. Now, independent variable here is that this guy. Independent means that the value you need to enter, and for clarity, we always assign the color blue, and this one and that is always the independent value you need to assign. And now, but this one has the dependent. And in this case, I would enter the in red, ES and EM. This is also a dependent variable, and this one is the independent. Okay, so all you need to do is that enter the number in blue, and all the others are, of course, a dependent. I mean, the calculate the values. In this one, also generally dependent. Okay, so this is kind of a summarize the what will be the given values and what will be the output we calculate. And the I can call this one is the constitutive equation is in a simple, say you have a stress strain relations. Okay, so fiber directions, this is the fiber directional stiffness, and this is the matrix direction, and so on. And I like to change a little bit like this, and I like to change, I'll say, give a more space here, and now this guy, that. Okay, so like to rearrange a little bit. So this one has the something fiber, and this one has the resin, and this is the something like the fiber volume fraction. So this one is the fiber constitutivations, and this one is the matrix constitutivations, and these are fiber volume fraction. So I would like to say that these regions has the fiber related properties, and this one has the matrix related property, so constitutivations. And here, like to increase the font a little bit. And this one also, and this is the calculate homogenize the stiffness. And we have another homogenized stiffness. So let's take a look at and let's try to drive them. But anyhow, I like to save this one. Okay. And this is the, by the way, is the one you have done as a homework, right? Very similar to the homework. Now, of course, we're gonna extend these terms like homogenized stiffness, or you can say UD or pry stiffness. And we will need another terms for Poisson's ratio or coefficient of thermal expansion and so on. So we will keep adding those terms, and along with derivation of a theory, and the let's continue to do that. But okay, it's a 2 o'clock, and let's have a 10-minute break. Okay, it is a 2:02. The class will start at 2:12. Okay, thank you. See you soon. And we after class we always upload our video and to YouTube so that you can review the class anytime for your convenience. That is also important because all the subjects in most of case is new to you. You may understand in the class, but to completely understand, you need to repeat. You need to repeat watching class, and you need to think repeatedly. Otherwise, the concept will easily disappear. It's very important. So make a full use of our YouTube class. I'm waiting for all of you. Turn on a video. Any questions so far? 질문을 듣고 싶은데. 한국말로 해도 좋고, 영어로 해도 좋고, 중국말로 해도 좋고, 뭐 중국말로 하면은 we have many Chinese. 그래서 중국 학생이 번역을 해줄 것이고, we have speakers. I mean, we can translate. I mean, any languages will be okay. 유영수. 아직 클래스에 아직들 다 안 왔나? 자, 수업 시작하겠습니다. 계속하겠습니다. 자, 그 다음은 Poisson's ratio를 공부해 봅시다. Young's modulus is relatively easy to understand, and there are many equations and courses you can learn about this Young's modulus, but the Poisson's ratio is relatively not much emphasized, but this is as important as the major Young's modulus. So we have to go through this procedure, of course, to consider Poisson's ratio. I mean, this effect has been neglected in one-dimensional case. We need to consider two-dimensional material properties. Poisson's ratio, by definition, Poisson's ratio, by definitions, we always have I would say, sigma for isotropy material. E always have I would say, sigma x, and then what? We always have the Poisson's ratio minus mu and sigma y. Sigma y. For example, we have some material, and this is the sigma x, and this is the sigma y, and something like that. I like to just remind you of this simple definition of the Poisson's ratio. And this is the extractional strain. So extractional strain will be caused by the stress in the same direction as x. So this sigma x will extend. Will extend, of course, this much, right? This much, we have an extractional strain, and due to this sigma x, and divide by the stiffness. And this extractional strain is also caused by the sigma y. Sigma y is the distraction. Usually when we apply the stress here, the original configuration is like that. And when we have a sigma in this direction, there will be always the contraction in extraction. So how much the contract? That's the definition of the Poisson's ratio here. So this much is again the amount of a strain in a y direction, and there will be a Poisson's effect, and that's the ratio is the mu, and so there will be a contractions like that. So that is the definitions of the Poisson's ratio. I just like to remind you of the definition of the Poisson's ratio. And this is for the case of the isotropic material. Now, for Poisson's ratio in extraction, in composites, imagine that this composite also are matrix and fiber and matrix and fiber and so on. Now we Poisson's ratio X means that we are applying the sigma X. Of course, we have a sigma X, but more importantly, like definition of from here, Poisson's ratio in extraction is the due to a sigma Y. So same in indication, same in composite, we have a sigma Y here, or certain Young's modulus, the strain value here. And then what we like to do, what we like to know is how much it contract, how much will be contracted here, right? That's the amount we like to know. And recalling the rural mixture, Y directions always given in terms of the fiber, in terms of matrix strain, there is the volume fractions. Again, remember that we have a certain length, certain amount of the strain that is the leading to a fiber volume fraction and matrix volume fraction. So in Y direction, the strain is given like that, and always the extractional strain is the given like that. In other words, fiber directional, matrix directional strain in extraction is the same as a UD. And so we simply put this equation here, put this equation here, and then these are all the same as EX. So we put it here and put it there, and so and this is the sigma X. But in here, when we calculate, I'm sorry, here, we have to consider this. This means that in fiber direction, okay, fiber directions, I'm sorry, this is not correct. In fiber directions, in fiber, there's a Y directional strain, and by definition of a Poisson's ratio, this is the fiber directional strain. Okay, this is the transverse strain, and this is the definition of the Poisson's ratio of the fiber. And same for the matrix. This is the transverse strain, and this is the amount of the strain in extractional strain, and this is the definition of the Poisson's ratio. Again, the fiber, back to here, the Poisson's ratio is always given like EX and EY. Well, you can say in this case, Y directional strain versus X directional strain. That's the definition of a Poisson's ratio for one-dimensional loading case. It's the same here. Poisson's ratio of Vm will be given as the EX and EM. EX, EY, this is the matrix, and this is the matrix. Same for the fiber. Okay, so we have these three strain, and this term, this one goes to here, because the y directional there are rule of mixture, and this one goes to here. I mean this there. Then this, now we have a x-directional fiber, x-directional matrix strain. These are same as apply stress, apply strain. So as you can see, we can simply have this is the final result, right? There is the volume fraction, there is the Poisson's ratio of the fiber, volume fraction of the matrix, fiber matrix, Poisson's ratio. And again, this EX will be the same as the, same as the, same as the, same as the extraction. So by definition, this will be defined as the Poisson's ratio. Again, EY versus EX is the Poisson's ratio of the mu x. So this is the Poisson's ratio given in terms of a fiber Poisson's ratio and matrix of Poisson's ratio. Okay, so let's get back to our equations. And Poisson's ratio, okay, here the constitutive equations, Poisson's ratio is given like that. And the homogenizer stiffness, only 3 terms, but I'd like to add here the Poisson's ratio, mu x, what we decide to call mu p Poisson's ratio x. And now what? This is the given as I like to show this equation. And here, look at these equations. Equal Poisson's ratio this times volume fractions of the fiber. Oops. Here, volume fractions times, oops, something. Volume fractions and the plus matrix Poisson's ratio plus matrix. Okay, so this is the fiber directional Poisson's ratio given in terms of a fiber and matrix. Okay. Now, you may wonder how can we calculate y directional stiffness? Well, we can certainly derive the fiber. I will draw here. We have this. I will say sigma y and sigma x. And the if from here we derive the Poisson's ratio x is given like fiber times VF and Poisson's ratio and volume fraction, right? And how about the mu y? Well, mu y we can derive, but there are a simpler way because by definition, in composite, even in composite, EY and mu y will be same as the mu x and EX. So this will be simply given as the EY times VX. So this is the something is not right. I don't know. Okay, using this equation, we can go back and we can say V Poisson's ratio here. I will say this one will be y, and this one we simply say, by the way, we need to give a name of this, and y, this will be defined as this, this times EY, which we already have it, and divide by the EX, which we already have. Oops, we didn't have a name here. We didn't have a name here. Okay, so this is the how we calculate y-directional Poisson's ratio. And as you can see, x-directional Poisson's ratio has the much larger than Poisson's ratio in y directions. Okay, let's continue. And basically that is the equation, meaning that homogenize the stiffness. So we have these 5 terms. Basically, this is the A dependent. We don't have to use that. But the okay. So here stress-strain relations. This is the 1 of EX. Here is the 1, minus Poisson's ratio divided by EX, and this one divided by EY, and this one divided by the EX. Okay, what it is that I will show the equations, which we will define in next class. And as you can see, this is the equations of the stress-strain relations of composites. And here you can call, you can use this one as the, actually same, but the, well, that's not so important. Okay, so this is constitution. What it does is that when we have stresses in UD, we can calculate the strain directly from these equations. So here again, this is the a compliance matrix, because for example, this is given as EX, and this is the given as EY, and so on. So this is a compliance, and what it does is when we apply the sigma, then we can have the strain. So this is the UD stress, and this is the UD strain, and this UD compliance, or in engineering constant, is the given as the fiber and matrix. properties through micromechanics. So later, when we have this ply stress, we can easily calculate the ply strain, or when we have a strain, we can simply multiply the stiffness matrix, and we can easily calculate. This C is simply the inverse of this compliance matrix. So please, this is a very fundamental but very critical procedures. Given fiber matrix properties, and you would have the compliance matrix, then you would have a stiffness matrix by inverting this compliance, and then you have a stress-strain relations. Okay, so again, I like to emphasize how important this is. This is from this definition, and this one comes from all the fiber property and matrix property, and then Poisson's rate volume fractions. Okay. Now let's take a look at the CTE. CTE is the coefficient of thermal expansion. Any material will expand somehow by temperature increment. And definition of a CTE is that the strain, the ratio of the strain and temperature, that is called CT, coefficient of a thermal expansion. Also like to remind you that definition of a CTE is like strain is always given like sigma E, right? That's the strain due to stress, but always there's additional strain due to temperature increment. Temperature increment, delta T, and there is the CTE. So alpha is the ratio between strain and temperature increment. And if we here, so in terms of the stress can be given in terms of a strain and alpha delta T. Of course, this is the most one-dimensional temperature, stress, strain relation, but this is the fundamental equation we need to fully understand. So this strain is basically a total strain. Total strain means that the strain we observed, that strain, this is also a total strain. The total strains can be derived by or caused by the external stresses. So this is the stresses in terms of a mechanical stress, and this is the strain caused by the thermal increment. And so in this equation, total strain minus the thermal means that we got the mechanical strain and then multiply by the E will give us a mechanical stress. Okay, so keep that in mind. And now look at the composite where we have a fiber and matrix and something, like this combination. Now, overall composite subject to a delta T. Okay, delta T is the external temperature. Regardless of stress, regardless of temperature, this composite has to increase the same amount in the x direction, right? That is given Ex. So that is the one we have to have it. Now, very importantly, the